Hi guys, this is Mike Mancias with Electrical Engineering 140. We have a problem with a thin ring laying on the XY plane, and the center of the ring is at the origin. It's carrying a non-uniform charge density lambda equaling alpha cosine theta, where alpha is a constant and theta is the usual angle defined with respect to the positive x-axis. Our task is to find the electric field at some distance z away from the center of the ring. So when we're dealing with problems like this, you want to use your Coulomb's law. And Coulomb's law is defined as you got some E field, it's a vector, and it's equal to Q all over 4 pi epsilon naught r squared. And this is also in our r hat direction. Okay? So this can also be written as, instead of having the 4 pi epsilon naught, you can also tidy it up a little bit by writing it as kq over r squared in the r hat direction. So yeah, the important part to note though is that this E field is a vector. It's a vector, and it's pointing in the r hat direction, wherever this point of interest is. Okay, so that can make these problems kind of tricky. So for example, let's say I had some charge, positive Q, and this charge is radiating some E field outward, right? It's positive, it has an E field pointing outwardly, and we are interested in the E field at some location over here, okay? And we want to see what that E field is doing exactly at that location. What is the E field doing through that point? Which direction is it pointing? So currently, at our point of interest here, at our point here, the E field is pointing where this red arrow is, right? It's pointing in that direction. And if we wanted to use our Coulomb's law, we would just say that the E field is equal to K, and we said it was positive Q. And we're going to just go ahead and say that this distance from here to here is called D. So instead of r squared we have up here, we're going to say it's d squared, because that's the magnitude of the distance from our charge to the point of interest. And this is still going to be pointing in the r hat direction, and that's basically just saying, where is the E field pointing at this point? Well, it's mostly pointing in this direction. In some cases you'll have multiple components. It could be pointing in different directions, but sometimes a lot of components will cancel out, and you'll end up with it just pointing in one direction. For example, if I were to elaborate on this, so now let's add another charge over here. This one's going to be a negative charge, and we're going to make these lines blue because it's negative. And they're not pointing outward, they're pointing inward. That's what negative things do. They point at themselves, right? And if we want to see again, what's this E field? What would the E field be doing through this point? Be pointing this way, right? And we're going to pretend like I drew this perfectly symmetrically and that these two distances are equal. And let's just break this up into its components, and we can see how these vectors are behaving with each other relative to that point of interest. So I'm going to draw the components in green here. So I have a component of the red vector pointing this way. And I have another component of it pointing downward. And I have a component of the blue vector pointing downward. And again, I got one pointing to the left. And so, like I said, we're pretending like I drew this perfectly. And if I did, then this length here would be the same as this length here. And they are pointing in opposite directions. And for that reason, these guys would just cancel out. And these vectors are both pointing downward in the same direction. So they would sum together and point down. And so the E field, due to these two vectors, overall, is just pointing downward. Okay, and I just wanted to give you guys an example of that. But our problem is very different than that, right? We don't just have point charges. We have a line of charge. Not only that, it's not even the worst part or the best part, depending on how you're looking at it. It's the line of charge isn't even constant. It's changing throughout the whole ring. So what does that mean? So first off, how do we write this? How do we write this equation in relation to a linear charge? So, basically, when you are doing problems like this, you're going to break it up into tiny, tiny, infinitesimal pieces. And these little infinitesimal pieces of charge, we're going to call them dq. And you can see we've got a dq there. And so it's just like it was in the previous problem. We have this dq. It has its distance r. It's got what's the E field doing at that point? It's pointing in this direction here, right? And it's got some distance r, right? That would be your r. That goes here. And but we have a lot of these, right? This is just one little teeny element of this whole ring, right? There's a lot more of that ring when you add up all those little pieces. And so when you're adding up a bunch of little pieces of something, typically, a little too far back there. Let me go. There we go. Okay. And when you're adding up a bunch of little pieces of something, you're going to use an integral typically. So we're going to write an integral here. We're going to rewrite our Coulomb's law equation in terms of for infinitesimal charges. So instead of E, we're going to have a teeny little infinitesimal E. And that's going to be equal, and that's not going to be a vector. We're just going to look for the magnitude of this guy. And, oh, shoot. Okay, and that's going to be given by, so we still have our K. That's 1 over 4 pi epsilon naught, just summed up into a K. And instead of Q, though, we're going to have dQ, an infinitesimal charge, just like we have drawn in the picture there. And luckily, the bottom is still the same. So we're still going to look at r squared for the distance away. And basically, the next step you want to do is find out how do you describe dq? What is this infinitesimal charge that we're talking about? And let's look at what we're given here. We're given that lambda. This has a non-uniform charge density of lambda equaling alpha cosine theta. So that's our charge. That describes our dq, looking at charge. And in the same way that you would take, if you were to take a density, say like a mass over a volume, usually it's given by meters cubed, and you were to multiply that by its volume, by its volume, then these would cancel out, and you would be left with the mass of the object, being kilograms, right? But this is a little different. So we're not given mass density. We're given charge density, and it's also not a volume, right? This is a linear charge density. So that means this lambda has units of coulombs per length. We'll say it's in meters. And so we're going to do something similar. We're going to multiply that by some length, and that's going to tell us what is the remaining charge. Okay, so that is the concept behind what we're going to do here. So we're going to say a linear charge lambda, and that's going to be multiplied by some length, right? We want to find the length of this entire ring here, right? So what's the length of that ring? It's just an arc length. What's an arc length? It's r, the radius, times the length of the arc. Now this arc goes around 2 pi, but we're not going to do r 2 pi, right? We're looking at tiny little pieces of the arc. We want a teeny little angle. So instead of doing r 2 pi, we're going to do r d theta, right? Infinitesimal angle, infinitesimal charge, right? Infinitesimal E field, infinitesimal charge. Notice that we have a d on both sides, and that's an important thing when you're setting up these integrals. And we can rewrite this with our dq and our lambda. Let's rewrite our lambda as alpha cosine theta times r d theta. Okay. And now we're going to take that and we're going to slap that up into our equation up here. So we're going to rewrite the dE as k lambda r cosine theta d theta all over r squared. Okay, so that that is basically your overall E field, infinitesimal E field. But remember, we want to look at these vectors, and we want to see how they're behaving in relation to our point of interest. So it's kind of hard to do with the picture here. So I redrew this, and we're going to look at it from a few different angles. So on the right here, let's start off over here. We're looking at it from the z-axis, looking into the ring, right? And remember, we have a linear charge density of lambda equaling alpha cosine theta. And you might have took note that the angle is in relation to the positive x-axis. So what that means is that you have, say, some vector this way, right, and pointing at the ring. And this vector, if it's going to move, it's only going to change angles in this direction. So you have some angle here, theta, right? And that theta means that as we get bigger, right, so what is that angle doing? As we get bigger, what's our charge doing? That's what we're trying to relate these angles and the charge together. And it says here that our charge is related to cosine theta. So whatever the angle is of cosine, or whatever the value of cosine is at that angle, will tell you how strong our alpha is. So when there is zero angle, cosine is the biggest, it's 1, and then this is just alpha. And then as we get bigger and grow out this way and go up towards the y-axis, we start to approach, what does cosine do as it gets up to the y? It goes to 0, right? Cosine of pi over 2, cosine of 90, that's a 0. So we have 0 charge there, right? And from that point, what does cosine do once it keeps going over to pi or over to 180? It becomes more and more negative till it reaches -1. So over here is going to be negative alpha. And then it's going to keep working its way around back to 0 and all the way back up to alpha. So just to give you a better idea of what the linear charge means, right? And keeping that in mind, now let's look at what these vectors are doing. Remember, these are all making, we want to break this up into a bunch of little DQs. And so these DQs would be vectors, or these DQs would have E-field vectors that are pointing inward this way, right? And the farther up I go, the smaller these vectors would be, okay? And they'd be contributing less and less and less until I got to here. And then on this side, I'd have tiny little vectors at the beginning, and then they get bigger, right? And then they get huge the closer you get to the y-axis. And then it would cycle back through all over again, bigger, smaller, right? You get the idea. So those are what your infinitesimal little E fields are contributing, right? And so, but we just want to look at 2 of those vectors, because every positive vector we have on the right, we're going to have a negative vector on the left. And so we want to see what those vectors are doing with each other. And so we're going to break it up into its components, just like we did with the example. And we got that we have a vector pointing down and a vector pointing in, and then another vector pointing this way. For so hold on, that was for this green is for the red vector there, and then for the blue vector, I have another vector pointing this way, and then one pointing up. We can see down, up, right? Remember this one? We just crossed those out because they're canceling each other out, and we're just left with a overall, when the components are all added up, then they're pointing in the negative x direction. And remember, these are just 2 vectors. So there are vectors all through here on each side, one pointing up, one pointing down, and every time the components are just contributing more and more and more to this direction. All those components just cancel out, and they just keep adding and adding and adding this way. So that means all the y components, everything in the y direction is just going to cancel out. And we're just left with the vectors adding up to the negative x position. Okay? And let's look at it from a different angle. Let's look at it from the top of the y-axis looking down. Now we're looking at x and z on the right side here. And same thing. I have a ton of vectors pointing out this way, right? And they're all adding up. But we're just looking at two of them, okay? So these two vectors have components, one pointing this way, and then another vector pointing down, to the left. And you can see this cancels with this, and we're left with just one vector pointing again in the negative x direction. So this means that even our z components are also canceling. Y components, z components, there aren't any. We just have negative x. Okay, so that kind of helps us out. Like, we don't have to look at all the vectors. We just need to look at the ones pointing in the negative x direction, because we know they all cancel out otherwise. So how would we describe this vector pointing to the left? How would we add up all those components? How do you describe the x components of this whole ring here? Well, if we were at the center of this ring, at the very, very center, if there were no z-axis, then we would be, if there were no z-axis, right, how would you describe all the vectors that are summing up and pointing this way? That would just be given by the value of negative cosine theta, right? Typically, your x components are equal to our cosine theta. But in this case, we're just looking at what the angle is that we're trying to point in these x directions. When you add up all those vectors, they're all going to be, the x components are going to be given by negative cosine theta. So we would be done with describing how these vectors are behaving with each other if there wasn't a z-axis. But we are on a z-axis, so we aren't at the very center of a circle. I don't know. We're over here. We're not here. We're not at the center of the circle. We're out over this way. We're way over at this point. Okay, so that means we got to look at this from yet one more angle. Okay, so bear with me here. We're just going to redraw this one more time. And I got my z-axis, and I got my x-axis. Actually, no, that's my z-axis. Sorry. And I got an x. So what's coming with me? You stay here. And then we have an x-axis going this way. Okay, and we'll line that up like that. Okay. And wait, we want to do this guy. Okay. And our ring is going around like so. And we're interested in, right, we're not at this location. If we were, then the overall vector, as we said, all the E field vectors. Here, I'll draw it really quick. If we were at the center, all these E field vectors would all be adding up and canceling out at the same time. You also have vectors pointing this way; they'd all cancel out, and you'd just be left with a vector pointing in this negative x direction if we were at the center of the circle. But we are not. Our E field vectors are pointing not towards the center of that circle. They're pointing way over here, right? This is our point of interest. Okay, so, and remember, we don't have just a couple of those. We have a ton of DQs on this, and each DQ is shooting a vector that way. And we also have vectors that are coming back this way. And what are all these vectors doing? They are all adding up and pointing in the same direction, right? They cancel out, and then the components that are left are, again, they're pointing this way, but we're over here, so they're pointing like this, all right? And so really, the ones that we need to be concerned about, we're pointing in the negative x direction. So that means when you add up all those E field vectors, they all add up, and you have one pointing like that, okay? And when you're looking at this, from from our point of interest, when you're looking at it from here, you're really looking at the shadow that this vector is casting on the xy plane, right? It's called the projection of this angle. And what is this line here exactly? How do we describe that with this vector? Well, it's the sine of the angle that it's making, right? And just I want you to imagine that you're shining some kind of light over here. You have a light bulb. It's shining, bing, right? And then as it's shining, it's casting a shadow, right? And so whatever shadow that makes, right? These were all the vectors. This blue vector was all the vectors that we added up together, and we just left with this one pointing in that direction, right? We said earlier that there was a vector, it was the negative x direction vector, but really it's the shadow that this vector is making from the z-axis from our point of interest. So keeping that in mind, yeah, this angle is just our, we're going to call that angle phi, and so the way that you describe that vector is with the sine of that angle. So earlier we said we had a negative, it's the negative cosine theta, that's still what we're talking about, right? We're talking about the negative x direction. This is our x hat, y hat, z hat. We're pointing in the negative x direction. It's still true. We still want that. But we also want to tack on the sine alpha. Okay? And what's nice about the sine alpha in this case is that it's constant. No matter whenever we are adding up our DQs, each one of these is all going to have the same distance away, and so the angle that they make with the angle that they make through our point of interest are all going to be the same, and so they all have the same value, and we can just take our definition of a trig function of sine, which is just opposite over hypotenuse, and the opposite of this angle is this line right here, which is your r. And then over the hypotenuse. Real quick though, let's say, just so you get a better idea of how we're using this, let's say let's say we weren't on the z-axis, let's say we brought this all the way back in, right? And let's say, we had a DQ here at this angle, and then let's say, oh, I want to be even closer, I do want to take it right here at the center. What's the angle right there? That's just 90 degrees, right? That's pi over 2. What's sine of pi over 2? That's just 1. So you would be left with just negative cosine theta, just like we said it would be, right? But since we are way out over here on the z-axis, we got to take the sine alpha into consideration, because it's not just the value of 1 anymore. Now it has some other value, but we can use the definition of it, and instead of writing sine alpha, we can write it as r over little r, right? Little r being our hypotenuse. Okay, that's it, guys. We can set up our problem now. And we are back here. So this was our DE, but we discovered through looking at our components and everything adding up, we're not worried about DE. We're worried about DE in the x direction. So I'm going to rewrite DE, and we're just going to worry about x. Okay, and we can carry everything else down that we just did. All right, but now we're going to tack on. Our newly discovered way of describing the x direction with our vectors from the z-axis, negative x cosine theta, r over little r. All right, and we can rewrite this even further and say that dE in our x direction is going to be equal to k lambda, and these r's combined to make r squared, and then that's going to be over this r with this r, that's r cubed, and these cosines combined, we're in the negative x direction, cosine theta d squared, right, the two cosine thetas, d theta. Okay? And we're pretty much done with what the problem asks for. It just says we got to set up the integral, but it's really not that bad once you use a couple of, or just slap one trig identity in there and it's good to go. So the trig identity is noted as the way that you describe cosine theta squared. One other way of saying cosine theta squared is use your double angle formula. Cosine of 2 theta all over 2 plus 1/2 is the same as this. That is another video that I'm not doing in this one, so you're going to have to hunt around on that. Hunt around for that one. But you can just take my word for it, and we'll do this integral here. And it comes out to be, so we're going to rewrite the whole integral. Let's just do it down here. So let's say the cosine, so we're going to, from dEx, we're going to take the integral of dEx, and we're going to take the integral of this side, because that's the only thing that's changing. Everything else is constant here, k, lambda, r cubed. None of that is changing. We're only looking at these dq's that we're adding up. Those are the only things that are changing. So it's just the angle that we have to take into consideration. So that means that we have the integral of this and this. What's the integral of cosine 2 theta over 2? Well, that's just sine 2 theta over 2, and this is going from 0 to 2 pi, right? We're going from this point all the way around right back to 2 pi, taking all those little dq's and adding them up, and we are left with sine 2 theta over 2 from 0 to 2 pi, and plus, what's that? Oh, this has a d theta at the end, right? There's a d theta with this, and a d theta with this part. So we can even say that this is also going from 0 to 2 pi. And what's that going to be? Well, that's just going to be theta over 2 from 0 to 2 pi. And we can plug in our values for our boundaries, and sine of 0, 0. Sine of 2 pi, also 0. So luckily, this is just going to cancel out. So theta over 0, that's a 0, and we're just left with this theta turning into 2 pi over 2. So what's 2 pi over 2? That's just equal to pi. All right, so that really simplified. And we can rewrite this whole thing. So the integral of dE, right, that's just going to be E. It's going to be our E field. It's going to be in the x direction. We'll make sure to take note of that when we're finished. And we have negative k lambda r squared all over r cubed. And we did our integral, right? We did all this. Cosine theta squared turns into this. We get sine. That just cancels out. We're left with pi. So we just tack a pi on there. Boom. And we are done with the problem. And this r cubed, if you wanted to, you can also represent this r cubed. This vector here is actually the magnitude of that vector is just x squared plus y squared plus z squared. And you can rewrite it that way if you wanted to. One other thing we want to mention is, remember, this is a vector. We better have an r hat in this direction. And oh wait, better yet, we know what direction we're pointing in. We're not pointing in r hat direction. We added up all our r hats, and we are left with the negative x direction. This is x hat. Okay? All right, so this is your answer for the E field for this problem, and hopefully that was helpful for you guys. And thanks for watching. Good luck with all your classes. Take care.